We're going to be going over the spring 2021 final question number 6, the query optimization. So part A is asking, estimate the cost in IOs of doing a full scan of our access plan for T in pass 1. So when we're doing a full scan of a table, that means we don't need to read through any index, no reading through any B+ trees, you just read how all the pages in the table itself. So from our table up here, we know that there are 30 pages in T. So that means the IO cost of a full scan is just going to be 30 IOs. In part 2, we're asked, now that we have a B+ tree with a height 2, unclustered, alternative 3 index, and the resulting tree has 20 leaf nodes, estimate the IO cost of doing an index scan on T.A as our access plan for T in pass 1. So now that we have a index scan, remember there's 2 parts that you need to consider. First, you need to do the IOs of reading through the tree itself. This includes traversing down the tree starting from the root to the first leaf node with the match, which in this case would be T.A equals 20. And then the IO cost of reading all the following leaf nodes until we reach the end of the table. Since we have a height 2 tree, this means we will need 2 IOs to traverse the root node and that inner node. And then we will need to calculate how many leaf nodes we have to read. Notice that it says up here that the selectivity of T.A is less than or equal to 20 is 1/2. Since the selectivity is 1/2, we include that selectivity estimate into our calculation of how many leaf nodes we read. And that means we only have to read half of the leaf nodes in the tree. So this will result in 1/2 times 20 IOs. And now all that's left is reading the actual data itself. Since we have an unclustered index, that means even if 2 records have the same key value, that doesn't necessarily mean they'll be on the same page. So we have to take 1 IO per every record we read. Since our selectivity again is half, that means we only need to read half of the records in the table, which would result in 1/2 times there's 30 pages in the table times 100 records per page, which is 1512 IOs. Part 3 asks, for this question, what are the following, for each of the following plans, which ones are going to be kept at the end of pass 1? Remember, the plans that are kept are ones that have the least number of IOs and ones that maintain interesting orders for later joins. When we're looking at table R, the interesting order is maintained by R.B, this index scan on R.B, because we have an order by on R.B later on in the query, so we want to maintain that one. The next consideration we want to take is the least number of IOs, and that's actually the index scan on R.A with 50 IOs. So that means option B and C are going to pass on for table R at the end of pass 1. If we're looking at table S, the least number of IOs comes from the full scan, and an interesting order for a downstream join is on S.A, because that's what's being used in these 2 joins over here. So this index scan will be maintained. So that means options D and E are also going to be kept at the end of pass 1. When we're looking at, when we're looking at table T, the least cost IO is going to be the full scan, which is 25 IOs. So we'll be considering option G. And T.A is also an interesting order for this downstream join that we have going on later. So we'll want to maintain option H as well. So the only plans not at the end, that we don't maintain at the end of pass 1 are going to be option A and option F. So part B is looking at the second and third passes of the query optimization process. So in part 1, we're asked, suppose that we choose a full scan on R and a full scan on S as our single table access plans. What's the estimated IO cost of a BNLJ join on R and S, with R as the outer relation and S as the inner relation? So for the outer relation, we know we need to read the entire table 1 time. So since R has 50 pages, that's going to be 50 IOs. And then for every pass that we read through the table S, we're going to read through each page and try to each block at a time and try to do as many joins as we can on tables R and S. However, since we know that we're doing R dot A is less than or equal to 50, we'll want to include the however many pages have, or take into account the fact that we have R dot A is less than or equal to 50, so we don't need to reiterate and read through all the pages of R every single time we do this inner loop of the block nested loop join. We only need to read through the 25 pages listed up here, which will actually match the join that we're trying to do. So the second argument of our BNLJ formula is the ceiling of 25 divided by b minus 2, which is 5 in this case, times each time we go through each block of R that we read through, we actually do need to read through all of S every single time, and S has 40 pages, so that's 40 IOs. And this results in, I believe, 250 IOs. So does the previous join, which is the block nested loop join in R and S, using full scans, produce an interesting order? And the answer to this is no. Block nested loop join does not create an interesting order, nor does it preserve any interesting orders as well. Which actually leads us into the third question. Suppose you use an index scan on RW as your axis plan with a full scan on S. Would it produce an interesting order? And again, the answer is no. Block nested loop join does not maintain any interesting orders. All right, in part 4, we're using a different query optimizer which follows this query plan, which seems to be materializing the scan of T after having done the selection pushdown. Assume that performing an index scan on T using the index T.A costs 80 IOs, and applying the selection on S.A takes place in the first pass of sorting S and the sort merge join algorithm. So using this query plan, what's the average IO cost of using the sort merge join on S and T with the unoptimized version? So in a sort merge join, first we need to, I'll just draw it all up here. First, we just sort the two tables, and then we need to include the cost of merging the two tables. So first, let's sort S. Looking at S, we have up here, we have 40 pages in S. So we're going to read in 40 pages. And we will distribute those 40 pages into runs and try to sort each run. When we look at our table, we're going to have 20 pages that match the selection that we're trying to do. So only 20 pages after we do that initial read are going to be actually streamed into what was written out at the end of this pass of the sort merge join. And those 20 pages need to be divided into runs, and we have 7 buffer pages. So that's going to be 3 sorted runs, because we take the ceiling of 20 divided by 7. But each of these sorted runs is going to be, we don't do any rounding up, so the total sum of how many pages in all of the runs is going to be just 20 pages. With 3 runs. Okay. So that was pass 0. Now in pass 1, we're going to take these 3 runs and merge them together into one. So we're going to read in 20 pages, and we're going to also write out 20 pages, 20 sorted pages. Now we're going to go and sort T. So the scan of T, as it says here, costs 80 IOs. So we're going to be reading in 80 IOs. When we do the selection pushdown of T.A, as it's, here. Okay. So when we do the selection pushdown of T.A is less than or equal to 20, that only leaves us with 15 pages. So after we do this initial read of the 80 pages of T, the resulting write is only going to have 15 pages in it. And those 15 pages, because we have this materialization step here, are going to be materialized into our table. And when we say something is materialized, that means you just have to write out those pages into your disk again. So we'll have the 15 pages here. these 15 pages are being written out and materialized into a disk. Cool, so now we have a sorted S, we have a sorted T. All that's left is to merge them both together. And that means we need to just read the two tables and do our pointers that we did in project 3 or 4, and just read through the tables one time and make them sorted. So this would result in the merge pass being 20 IOs plus 15 IOs. So our result is going to be 230 IOs, which you just get by summing 20, 40, 20 plus 20, 80 plus 15, and 20 plus 15. All right, in part 5, does the previous join produce an interesting order? So in this case, yes, it would produce an interesting order because the table that we were reading in, the table S, is the left table. And so an interesting order, it has an interesting order on S.A because we sorted it before we did our sort merge join. And since the S table was the outer table of our sort merge join algorithm, its order is going to be maintained or preserved, which means that this interesting order will carry on into the result of the sort merge join. So we will say, yes, it does produce an interesting order. And the reason we care, by the way, about S.A is because our main query that we're trying to execute has an S.A in one of the comparisons that it's trying to do with R and S at the next step. In part 6, assume you have the following IO costs for joining two tables together, and they reprinted the query here. Which of the following plans will be kept at the end of pass 2? Again, same principle, we want to keep the cheapest join, and we also want to keep interesting orders. So when we're looking at joining R and S, the least cost join is going to be this one here, part A, or option A. So we want to maintain that one there. The next option that we'll look at will be actually option B, because it produces an interesting order on R.B, and R.B is what we're doing an order by later on. So that's something we'll want to maintain as well. When we're looking at S.A, so since we have joined R and S, the remaining join that we would be looking to perform would be the join on S and T. And since we're joining on S.A, maintaining an order on S.A is actually going to be an interesting join for us later on, so that it would maybe make things go faster. So we'll keep option C as well. So far we have kept all the 3 options for joining S and R. Looking at option D, or looking at the choices to join T and S, we want to keep the lowest IO cost for that one because we do have to do that join at some point, and that's option D. But the other option for T.A unfortunately doesn't produce an interesting order because at that point we don't need to do any more joins on A, so we'll not consider option E. And options F and G join tables R and T, which we don't need to join in our query. So this would just be a Cartesian join or just a cross product, and we don't include those in the query optimization or system R query optimization. So we're just left with options A, B, C, and D. Now in part 7, we're looking at the passes that are considered for pass 3. At this point, we would look to just remember what we know about system R. We don't consider left deep joins and we don't consider cross products. So right off the bat, we can eliminate options, these last 3 options, because they're all left deep. Notice how the T is on the left side and the ones that are in the parentheses have been joined already. So that would be considered, these are considered right deep. So ignoring the last 3, looking at the first 4, we don't want to include any Cartesian products. So we don't want to have RT again, for the same reason that we eliminated it above. It's a cross product. Lastly, we'll look at the first option, which is joining R and S and then joining T. So this one we'll want to keep because we know that we need to join R and S, and at that point we know we need to join with T. So we'll want to keep this one. When we're joining SR and then joining it with T, it's not considered because if we remember what we considered at the previous step, the join on SR was not considered because SR was not retained at the end of pass 2. Wow. Okay, so we won't consider this one. And then when we're looking at joining S and T and joining that with R, there's no obligation to doing this, or there's nothing wrong with doing this because we have maintained the order on S and T, and we know we need to join S and R at some point, so we want to keep that one. So the only two that are going to be considered are the first option and the fourth one. We'll skip question C because it was particular to last semester, but the lecture that Brian gave on MongoDB is in scope for the final, and you will expect to see something similar to this. So make sure you either watch the lecture or study your notes for that as well. Okay. That's all.